Okay, can you see the slides? Nampak ke? All right, good. All right, so today we are going to learn about PN junction, right? The basic of PN junction. So this topic requires the previous knowledge that we've learned before, like carrier transport phenomena and generation and recombination, and also the previous topics like Fermi level, Fermi energy, Fermi drag, distribution function, density of free electrons, free hole, density of states, and stuff like that, right? So it's going to require all those basics from our previous topic. So as usual, before we move on to our new topic, let's recap on what we've learned in the previous topic. So let's go to the first one. What is carrier diffusion length? Anyone? What is diffusion length of carriers? You can unmute yourself. You can write down in the chat box as well, as usual. We learned this yesterday. So apa diffusion length? Cornelia, how about you, Cornelia? What is carrier diffusion length? Go on. Someone, please. Okay, Juaria said average length a carrier moves between generation and recombination. Akila said distance from generation and recombination. Yes, good. Right, so distance traveled by a carrier, so either electron or hole between generation and recombination, right? Distance travel. So that's carrier diffusion length. Right, so let's continue to the second one. How do we calculate diffusion length? What is the equation involved? Okay, Farid said L equals to square root D times lifetime, okay? L equals to square root D tau, right? Diffusivity times carrier lifetime, right? Third one, why recombination takes place at the surface of silicon? Cornelia, internet connection is not okay. Okay, that's all right. Okay, no problem. Okay, why recombination takes place at the surface of silicon? Why do we have surface recombination in this case? So I did explain yesterday about the surface recombination. Why do we have surface recombination? Anyone? So you have to be clear of all this stuff, okay? Because the moment we go into PN junction and devices electron, all of these are going to be required. So why surface? Why do we have surface recombination at the surface of silicon? Anyone? Okay, sebab ada severe disruption to the, yes, disruption to the, kat mana yang ada disruption tu? Crystal lattice, right? So disruption to the lattice. Why do we have disruption to the lattice? In this case, what is the one possible reason? Well, there are many more, but what is the most obvious one, for example? Why do we have disruption? Kenapa? Okay, that's fine. Anybody else? So I have the wafer now with me since I'm now in the office. So dekat surface ini, surface depan ni, here and at the back, by default we're gonna have tak nampak pula due to the background. Hold on. Oh, sebab di color sama, so wonder. Well, just the front side then. Okay, by default you're gonna have front recombination here, front surface and rear surface as well. Termination of lattice because the way we produce the wafer is by slicing silicon ingot, right? Ingot tu macam bantal yang panjang tu, bulat panjang. So to be able to have wafers, you have to slice the ingot. We're gonna learn the slicing process in 487 for applied student, right? So the slicing process introduces defects. If you imagine, for example, if you have a log, macam kayu balak kan, kayu kecil. If you want to cut, for example, if you want to cut the log into pieces macam salami kan, macam wafer lah. So bila you potong nak dapat satu keping, one piece of that log, then what's going to happen between one to another? You pakai gergaji yang electrical tu, yang auto tu kan. Potong tu apa jadi? Bila you potong nak dapat satu slice yang kecil, for example, you're gonna have habuk-habuk kan in between, right? You akan potong between kan, you akan dapat habuk terbang-terbang kan. So you're gonna have dust flying everywhere, right? So while cutting through the slice, while cutting through the log, you're gonna generate defects due to the interaction between the chain, the saw yang you guna tu, dengan the surface of the silicon ingot, right? So you macam kasarkan dia as if you are rubbing the surface to be able to produce one piece, another piece, another piece. So this rubbing process, the cutting process, interacts with the surface of the silicon of both sides for every single piece. So that generates some defects. So that's why you will have surface recombination. And this is not the only case for silicon. We will also have some other cases as well. When we learn about 487 in deposition process, if you do a chemical vapor deposition or sputtering or evaporation, you also are going to have a surface recombination issue on the deposited layer, on the surface of the deposited layers, right? So, but don't worry about it yet, but this is the basic that you need to know at this point. Combination at the surface. So the moment you have defects on the surface, I told you yesterday, defects are physical in nature, but in the band gap, they appear as electronic states. They are the satu energy level dalam band gap, right? In the forbidden gap. So the moment they appear in the band gap as a trap state, they will capture your electron hole, right? So there will be recombination centers. So that's why they have to be fixed. The defects have to be fixed by a process that we've discussed yesterday. Right, move on to number 4. Do we want our SRV to be low or high? Why? We discussed this one yesterday as well. Surface recombination velocity. How fast the carriers move to the surface for recombination process. Do you want them to die fast or die slowly? Because recombination is annihilation process. They will be gone from the system. So do you want them to die fast or die slow? Die fast means high SRV. Die slow means low SRV. Yes, you want it to be low. You want SRV to be low, right? So if you have a high SRV, that means the surface recombination is very high. On the other hand, if you have low SRV, the surface recombination is low, right? So that's how you tell whether a surface recombination is high or low by the SRV. High means bad, high recombination. Low SRV means okay or good, less recombination. Okay, so that's how we tell. Right, next, how to fix defective surface and bark in order to reduce carrier recombination rate. Remember yesterday we've discussed that we have surface recombination and also bark recombination. Surface recombination on surfaces and bark recombination in the bark, right? So this one's surface, other recombination, surface, other recombination, and bark is in the volume. Bark means in the volume, right? In the volume of the material, silicon or whatever. So you have surface recombination here, surface recombination here, and a bark recombination here. So that means the electron and hole recombine here in the bark and recombine here at the surface after the generation process. So how do we fix that? what is the process name that we have to do in order to fix both defects, in order to suppress recombination rates of both processes? What's the process name? Anyone? Right? Okay, good. Surface preservation. Okay, it's called surface preservation. Surface preservation is to suppress surface recombination, and bark preservation is used to suppress recombination in the bark. So generally, you can call the process. Generally, you can call the process as preservation, the general name. So what it does is it will fix the dangling bond. Dangling bonds, they can saturate, if you like, saturate dangling bond, because the moment you have terminated lattice on the surface, you're going to have bonded not fulfilled, bonds that are not fulfilled. So what we'll do on the surface is we will saturate the bond by connecting the dangling bond to some other, to the new atoms through the new process, right? So this preservation can be surface preservation to suppress surface defects, and it can also be bark preservation in order to suppress bark defects. Okay. Okay, so this is the gist of the previous discussion, previous topic. Okay, so if you're okay with this, then you should be all right with the previous one. So now let's move on to our new topic, which is on PN junction, right? So PN junction is the transition topic that you have to understand before we move on to devices, right? So we've learned about materials, the physics side of the semiconductor material, and then now we're looking at forming a junction. And next, after the mid-sem break, I think we're going to look into various semiconductor devices. Okay, so that's why this topic, this subject is called physics of semiconductor devices. You learn the physics in the first half, and you learn about the semiconductor devices in the second half, right? Without the physics, you won't be able to understand completely or successfully the semiconductor devices in the second part. So in this topic, we're going to look at introduction to PN junction. We're going to look at PN junction at thermal equilibrium. Okay, so you have to look into thermal equilibrium condition first for every condition. Like last time, before you introduce excess carriers, you have to understand the thermal equilibrium condition first, right? The P naught and N naught, Kp, N naught, and P naught. We've discussed that before. So before we introduce delta P or delta N, excess carriers, into the system, into the semiconductor, you have to always understand the thermal equilibrium first. So the same goes to the PN junction. Before you understand what we call the mechanism or the effect of external factors acting on the junction, you should be able to understand what is happening at the PN junction under thermal equilibrium condition first, right? So next, we're going to look into PN junction under applied bias. So the moment you understand what happens to the junction under thermal equilibrium, you then have to understand what happens if you apply some positive voltage or negative voltage to the PN junction, right? What is the effects of applying either positive voltage or negative voltage to the PN junction that was originally under thermal equilibrium condition, right? So the bias here means the positive or negative voltage, right? Positive or negative voltage, right? So we'll see what's the effects of both voltages. Then we also looking at a PN junction with illumination, which is partly learned in generation of excess carriers, right? So we've learned about generation of excess carriers by a couple of methods like illumination, like electron beam bombardment, and also by doping, right? So we're going to look into the very same thing, but in PN junction setting instead of in a P-type only or in N-type only, right? So, and eventually we're going to look into applications of PN junction briefly before we start going into semiconductor devices in the second half. Right, a PN junction forms the basis of many semiconductor devices such as solar cells, LEDs, lasers, photodiodes, BJTs, bipolar junction transistors, JFET, junction, field effect transistors, and many, many more semiconductor devices. So these are among the illustrations or the pictures to show the applications of PN junction, right? So you can see here solar on the roof. So this is the roof of my previous school when I did my PhD at UNSW in Sydney. So the school has about 150 kilowatt of PV system on the roof, feeding the electricity into the building, right? To cater some parts or some portion of the energy consumption every month, right? So in the second one, you can see LEDs of different colors, which is also based on PN junction, and you can also see lasers, right? In the third one. So we're going to see each of these later on as we move into semiconductor devices. And we're going to look into the principle of operation, how does each work, and what is required for each of the device to operate properly. So what is a PN junction? Okay, so we have learned about a P-type semiconductor material on its own. We've also learned about N-type semiconductor material on its own. And for each material, you have learned about majority carriers, concept of majority carriers, and also the concept of minority carriers in each P-type and N-type, right? P-type and N-type. Now we're looking into combining P and N-type together to form a junction, right? So a PN junction is a boundary of interface between two types of semiconductor material, P-type and N-type. We are combining P-type and N-type inside a single crystal of a semiconductor. Okay, so this is a general definition of a PN junction where you will have P and N polarities combined in a single crystal of a semiconductor material. But later on, we're also going to look into what if we form P and N junction from two different materials. Okay, so for this default definition, say we are looking at crystalline silicon composed of P and N, right? But both are made of crystalline silicon, originally crystalline silicon, so that's why they are called as a single crystal lattice. But later on, when we learn about other sort of junction, other type of junction, we're going to look into combining, say, P-type of crystalline silicon with N-type zinc oxide, or P-type of cadmium telluride with N-type zinc oxide, for example. So in that case, we're going to form different type of junction. Okay. So when you form a P-N junction in the same material, using the same crystal structure and band gap, we're going to call this as a homo junction. Homo junction. Homo means same, right? Same material. Next, we also are going to learn about another sort of junction. So what is the opposite of homo? Still a junction, but what do we call that? What do you think? If we combine two different material, is called heterojunction. Okay, so say if you combine crystalline silicon with zinc oxide, crystalline silicon with cadmium telluride, crystalline silicon with whatever, or it can be gallium arsenide with whatever, then as long as you have two different material of different crystalline properties and band gap, of course, so you're going to call that as heterojunction. Okay, so in this case, let's look into homojunction only, right? So one region is doped with acceptor impurities. So we learned about Na concept, which makes the semiconductor P-type, and the adjacent region is N-type, which is dominated by Nd. Right, so you're taking a semiconductor material, say crystalline silicon with Na or P-type, and another one with Nd or N-type. So it combined together. The interface separating P-type and N-type is referred to as metallurgical junction. So this interface is called metallurgical junction, right? So what exactly happens when p-type and n-type materials brought together to form a junction? So previously we learned that we know that when you have a p-type material, p-type crystalline silicon, you have holes as the majority carriers and you have electrons as minority carriers, right? So the level of holes as the majority carriers depending on Na, right? We've discussed before, the density of hole is given by Na, and we assume that the material experiences 100% ionization. Therefore, P is equal to Na. And on the other side, the density of electrons, which is the majority carrier, is equal to Nd. And we've also learned that in the p-type material, you also have minority carriers, right? Minority carriers. So how do we calculate minority carriers? In this case, say for n-type on the left side, how do you get the value of n in the material on the left, in the p-type material? What's the equation that we need to use? Anyone? Remember law of mass action? Apa equation? N times P equals to Ni squared. So you know the, yeah, okay, good. So you know the P equals to Na, now you want to know the N. So the N will be then equal to Ni squared over P, right? Ni squared over P, or Ni squared over Na, same thing. And the same thing is applicable to the N-type as well, right? Ni squared over majority carriers will tell you the density of your minority carriers. So that's clear. So what will happen next? We're going to see later on when you combine a p-type semiconductor and an n-type semiconductor, we're going to see our majority carriers diffusing to the neighboring regions. Okay, so our p-type has holes as a majority, our n-type has electrons as majority carriers. So what will happen is our majority carriers will diffuse to the neighboring region. Diffuse to the neighboring region. Why do they diffuse to the neighboring region? Why do we have that diffusion in the first place? Recall back what we learned in carrier transport. Why do you have diffusion? Anyone? Excess? No, not really. Equilibrium is the result. Yeah, so that's the word. Different concentration, right? Sakina, good. Different concentration, or we can also say that. Why? What do you need to have in order to have diffusion? Concentration. Apa? Yes, high to low, of course. What's the exact word? Concentration. We learned last time, to be able to have drift, you need to have electric field. To be able to have diffusion, yeah, concentration gradient, right? Concentration gradient is the word. Pardon my writing. So you need to have, due to the concentration gradient, when we pair the p-type and n-type material, hole in the p-type sees that there's no hole or so little holes in the other side of the junction, and electrons here in the n-type see there's so little electrons in the ends on the other side of the junction. So holes see a concentration gradient while looking into the other side, and electrons see a concentration gradient as well while looking into the other side. As a result, we have hole diffusing from p-type into n-type. Majority carriers, dia akan ke sana in order to establish thermal equilibrium, and at the same time we're going to have majority carriers in n-type electrons diffusing into p-type, because they also see concentration gradient, right? So you're going to have a hole diffusion into n-type and electron diffusion into p-type. Okay. So in our case, for simplicity, we assume that the junction is uniformly doped. But in real cases, we may have cases where the junction is not uniformly doped. But for the sake of learning the theory behind the fundamentals, we'll only assume that the junction is uniformly doped. And we'll also assume that the junction is abrupt in nature. Abrupt itu maksudnya ada perubahan yang sudden lah. Sudden. So if you're talking about electrons, a hole, for example, we're talking about this abrupt change. Maknanya yang almost macam tu lah. If you're talking about like this, then it's not abrupt. That's not abrupt, but this one is abrupt. So sudden change. Okay, so we are assuming abrupt change at the junction for simplicity. So once joined, electrons, excess electrons in the n-type material. So remember, so you have to be clear on the concept of majority carriers and minority carriers in both types of semiconductor material, p-type and n-type. So electrons in n-type diffuse to the p-type and excess hole from the p-type diffuse to the n-type due to concentration gradient. So you learn this now, concentration gradient, due to concentration gradient. Okay, movement of electrons to the p-type exposes positive ion cores. So the moment you have, so this one is p-type, this is one n-type. So you have so much holes here, so much electrons here. So when the hole is diffusing to n-type, so it's going to leave negative ion cores, negative charges near the junction. And the same thing happens to the electrons. So when electrons diffusing into the p-type they're going to leave positive charges near the junction, fixed ion charge that are not moving. Electrons and holes are moving, but the ion charges are not moving because they are left by electron and hole. Okay, so you're going to be left with fixed ion charges, positive side and negative side near the junction as a result of diffusion of both carriers into both regions. Okay, so movement of electrons to the positive side exposes positive ion cores here, and movement of holes into the n side exposes negative ion cores here in the p side, resulting in electric field. So since we have fixed charges that are not moving, you're going to have built-in electric field set up at the junction due to the presence of the positive and negative ion cores and forming the depletion region, right? This region in the center near the junction is called depletion region. Depletion region. Why do we call it depletion region? Because it's depleted of carriers. Carriers dekat junction tu dah masuk dekat opposite region. As a result, the region near the center, near the junction, is depleted of carriers. Hence, it's called depletion region. As a result of the electric field, we're going to see later on, as a result of the electric field, you're going to have built-in voltage across the junction, VBI, built-in voltage across the junction as a result of electric field at the junction. So let's look at this animation before we end. Sorry. Okay, let me open the website. Saya punya open pula terbuka. Okay, let me go back to the link now. Oh, error. Kenapa? Yeah, we open PN junction. Okay. Right, let me share the website now. Okay, can you see the PVC ROM website? Apa? Okay, good. So this, you can come here at the PN junction is, all right, 3.5. You can go to PN junction. So this is a brief definition of PN junction. You can come to this PN junction. Next. So this is the same thing that I explained in the slides now. So let's look at this animation here to see what is actually happening. So with the p-type and n-type material separated by the carrier, diffused around randomly, right? So remember that the boundary, the metallurgical junction here is imaginary in nature. It's not like physical junction, but it's imaginary junction, imaginary border, if you like, right? Holes are on the p side. Holes are the majority carriers on the p side, left hand side, and electrons, red one, are the majority carriers in the n-type material on the right. Okay, so let's next. Okay, so now they start diffusing. When they are joined together, you can see that the holes in the blue region now diffusing into the pink region or the red region to the right. And at the same time, we have electrons on the right as the majority carrier diffusing to the left because of the concentration gradient as well, right? So as a result, you have fixed ion charges right in the middle near the junction. Okay, so note that you have negative charges on the p side as a result of holes leaving the region, and you're going to be left with a positive ion charges in the n side as a result of electrons leaving the region. Okay, electrons leaving the region. So this is only, if you look at this schematic, it's only covering the region near the p-n junction. So if you look at my cursor here, my mouse cursor, so this blue region, the whole blue region, is only the region near the junction. Okay, it's not the entire p-type material. So you still have another material on the left hand side of the blue here, but it's not shown as part of the junction. So you're going to have like p-type material to the left of the blue region, and we also have n-type material to the right of the red region actually. But this illustration only shows the region near the junction. So note that the region to the left of the blue and the region to the right of the red doesn't have the positive and negative ion charges. Instead, they are neutral in nature because they are not near the junction, right? As you go away from the junction, so the materials are going to be neutral in nature, just like the original condition, as if they are not combined together. So the changes only happening right near the junction. Okay, if you go away from the junction into p-type and into n-type, they are neutral in nature, right? So due to the positive and negative regions near the junction created, we're going to have electric field pointing into the p-type region. Okay, you can see the arrow here pointing to the left into the p-type region. When the materials are joined, carriers cross into the other region. However, the fixed ion charges that are left behind set up an electric field. Next, the electric field tends to keep the holes in the p-type and electrons in n-type. However, okay, hold on, ada kawan kat sini waiting to join. Okay, on the end. Okay, however, even at thermal equilibrium, some carriers have sufficient energy to cross the depletion region. So the moment you have, okay, if you record now, when you combine, you're going to have diffusion of holes into n-type, diffusion of electrons into p-type, and then we're going to have fixed ion charges near the junction. As a result, we're going to have electric field, and this electric field will keep the original carriers, holes in p-type, electrons in n-type, in the original region from further diffusion process, right? So the moment you have the electric field, the holes in the p-type will not be able to cross into the n-type anymore, and the electrons in n-type will not be able to cross into p-type anymore, just like what they did when they are combined few steps back, right? So now the holes will stay in the p-type material as original condition, electrons will stay in the n-type material as the original condition due to the presence of electric field. This electric field will actually set up a barrier height. Macam you ada tembok lah, the moment you dah sampai thermal equilibrium condition, you're going to have electric field set up and built-in voltage set up across the junction. And this is seen by the electrons and holes as a barrier. You macam ada tembok for the electrons and holes to cross. So they are not able to cross anymore because the barrier is built right in the front at the junction. Unless they can overcome the barrier, they will not be able to cross the junction. But however, at some condition, okay, for example, at thermal equilibrium, or if you give heat to the system, if you supply heat to the system, some of the carriers will be able to cross the barrier because they have excess energy, or they have more energy than the barrier level. So the energy is higher than the barrier energy that makes them pass across the junction again. But at thermal equilibrium, they will not be able to cross the junction anymore. Okay? So that's what it is about thermal equilibrium condition. Let me go back to the slide before I finish. Okay, you can see the slides, right? Right, good. So you've seen animation, so that's what's actually happening when you have the diffusion. Okay, let's just finish off on this slide. So the majority charge populations are approximately equal to the doping level. So we've discussed this one before, and I've just reiterated the very same concept as now. So in the p-type, the doping level, the density of a hole as the majority carrier will be equal to Na, and in the n-type, the density of electrons, which is the majority carrier, is equal to Nd, right? So in thermal equilibrium condition, you can use this P, the P density of hole as majority too, you can use it as PP naught, right? PP naught here means density of holes in p-type material at thermal equilibrium. So three things, right? Three facts. Density of holes in p-type material at thermal equilibrium equals to Na, and the same thing goes to n-type. N equals to Nn naught. Density of electrons in n-type material at thermal equilibrium is given by Nd, your doping level. As a result, now let's look at minority carriers from the law of mass action. Minority carriers will be, if you look at this, just look at p-type first. Look at one by one. Look at p-type first. Np naught is the minority carriers in the p-type material, in the blue region, yeah? So that's given by Np naught, or density of electron, because electron is a minority carrier in p-type material in the blue region at thermal equilibrium, right? So that's given by law of mass action, Ni squared over Na, or Ni squared over Pp naught, since Pp naught is Na, right? So the same thing goes to the right region as well, n-type. So the minority carrier in the n-type is electrons, is hole. Therefore, the hole as the minority carrier is given by Pn naught, right? Pn naught, density of hole in n-type material at thermal equilibrium, is given by Ni squared over Nd, or Ni squared over Nn naught, right? So moving on, you should be able to understand and use the concept of Pp naught, Nn naught, Np naught, and Pn naught, right? So because we're going to use this one a lot after this, in thermal equilibrium condition, under applied bias, and some other condition as well. So make sure you understand the concept of majority carriers and minority carriers using these new notations, right? So I think that's all for today for the introduction to PN junction. We're going to continue tomorrow on what happens in the PN junction at thermal equilibrium. So is it okay so far? So can follow so far on the concept of PN junction, the introduction, the diffusion, built-in electric field, space charge, depletion region. Yeah, clear, good. Any questions? Ada? Right then, I'll see you tomorrow then. Bye-bye. Thank you. Assalamualaikum. Take care.